station. So this is around the Seattle area, and we're looking at like 5 megawatts of power in the high end being transmitted out. And so I'm going to look about what could you actually do with that. You know, if we use this pre-transmission or path loss equation, you can calculate how much power you have. So you see at different distances away from the reader, or from the transmitter, you actually have different amounts of power available. So if you create a device that's going to use this, you have to have a device that will actually adapt, or you have to go with the lowest functionality power load. So you could have different modes of operation. I'm close, I can use more power, do more things. When I'm far away, I have to kind of slow down activity. So we made this device here. We just have this off-the-shelf silver flyer digital TV antenna, and basically the front end of a WISP, and we tuned it a little bit specially, and just took some measurements. So from Intel Research Seattle, we can get, and it's about 4 kilometers away, we can get 60 microwatts of energy. So Free's equation would predict like 280. So we're losing some certainly in conversion, but that's enough to run a WISP. That's enough to run duty cycled WISP. That's enough to run RFID. So now we have this usable power we can get out of this. So here's some experimental results. We have this power station, weather station. So it's 2 temperatures and humidity, and we're running it continuously off of the station that you can see in the background there. So this thing can stand up and work forever. I also made this for Intel research at Intel Day. I made this, this basically calculator cannon that you can go and point at the towers and do some, calculations. So I made it more portable, and you can use it anywhere. So I think this really opens up this new idea of how we can harvest energy. It's no longer I'm going to set up the infrastructure and set up a base station. I can really use these TV harvesting. So you can imagine that if I have something that can use multiple channels, these frequencies are fairly close together. You can look at the surface area or the coverage area that I can get to run devices. So if I have, the caveat here is I have to have line of sight. I made it really small so you guys wouldn't notice. But I have to have line of sight to my transmitter. But there's a lot of power there to be used. And I certainly think the census community could probably do something with that power. So I'm going to switch gears. I'm going to talk about the high power stuff that I've been working on. This is called WREL, Wireless Resonant Energy Link, and we'll just play this video here. So, good's playing there too. So we see we're lighting this light bulb. So we have this transmitter on the side here, making this oscillating magnetic field, and we're basically being able to catch it with that light bulb and light this light bulb. So that's about 60 watts of energy. What's interesting about this technique is that, it's very efficient. So this isn't the same as inductive coupling, which has one of our cube fall off. This has actually a linear fall off, or it was constant efficiency, and then it starts falling off. So this new regime of having these coupled resonators. So this particular experiment can go out to about 3 feet, about 75% efficiency. So what are the components here? So we have an amplifier. This amplifier drives this loop, creating this oscillating magnetic field. We have this resonator starting to build the magnitude of energy stored in this resonator, starts building and building and building. And then we have this receive side that's a reciprocal. So we have a second resonator and a loop. So if you can imagine how a singer can shatter a glass with her voice, right? Her voice box is a resonant structure, a glass is a resonant structure, and over time it imparts energy over each cycle until the thing can break. So that's what we're doing here. We have these resonant structures that are making this tightly coupled system, and we're transmitting energy, over to the other side. Let's see. So we build a mathematical model of this, and there's some interesting things that pops out. So here we have, this is the coupling between the 2 main coils, which is equivalent to distance. And then we have a frequency on this axis, and then the magnitude in S1, 2, or S2, 1. So what we find out is that there's actually these multiple regions in which it operates. So we think about the overcoupled regime, and that's where this frequency splitting occurs. So the observation here is in this little red box that if you choose the right frequency, you can get back the efficiency. So if I was, say, at 10 megahertz but very close, there's no energy transfer in that area. But if I retune, out to say 11 megahertz, now I can go and transmit lots of energy. Right, so this is how we can use, wireless power transfer. There's this point called the critical coupling point, and that's the point where we cannot no longer hold the overcoupled regime, and that's when the 2 modes of this oscillator come back together, and now this starts falling off. So we think about these frequency splitting. If you had 2 pendulums that were, swinging back and forth with a spring in between, they either oscillate in phase with each other, we're out of phase with each other. So that's the same thing that's happening here, just with magnetically coupled resonators. So we took some experimental results. What we have here is, this is our experiment. We have a symmetric transmitter and receiver. The black dots, which are forming basically these lines, are S21 measurements taken at different distances. And then the mesh underneath it is, our predicted model. So you see, we have a slight over-prediction on the high mode, or the low frequency mode, and a slight over-prediction or under-prediction on the high frequency mode. So that's kind of due to this cross-coupling effects from the loops to the coils. So one of the things that I think is interesting is that, we can do this adaptive frequency tuning, which basically allows us to, if we think about other wireless power solutions, have like inductively coupled things where you set down your phone or something, and you set down in exactly this right place. Maybe there's magnets to help, get you in the right spot, and then you can have this inductively powered transfer. So same with your wireless toothbrush, right? So you have to hold it in one direction, but you don't have a lot of range, right? It's basically contact. You may have a few centimeters. So with this technique, you can basically have some extra range. It's not, it may be impossible, might be possible to get this entire room, but certainly we can do better than just one spot. And what we can do is use the frequency tuning. So here's a plot of distance versus efficiency. And if we just did a dumb approach, right, with no frequency tuning, just went out the center frequency, we'd see these blue dots, and then we'd say at very close, it doesn't work. If we select the right frequency, now we can have near constant efficiency. Now, my claim earlier was that we'd have constant efficiency, and it looks like it's falling off. In reality, what's happening is that the in-phase things are helping out wireless power transfer, helping out the transfer rate, and then the out-of-phase is actually hurting. So if you didn't have any of these cross-coupling terms, it would be constant, and then it would start falling off. The other interesting thing is if we go and set these things down, you don't have to have, this precise alignment. It's not like far field where you have to have these really directional antennas. If I'm off by a little bit, yes, there's the coupling coefficient changed a little bit. Now all I have to do is do some frequency tuning, and now I can get the maximum power transfer back. So you can see this is, degrees. So I can get out to about, 60 degrees off axis. So like that, and it's still going to have, good power transfer. So that's kind of range independent, wireless power transfer, range and orientation dependent. Okay. So some of the applications we're looking at and some of the future work here. So, 1 minute. I think we're excited, and I think Intel is excited about things like wirelessly powering laptops, cell phones, consumer electronics. And certainly that's an interesting workspace, and there's going to be a lot of stuff to get there. One of the things is that the entire system is one coupled device. Like far field, right? You have a transmitter, and energy goes out, and I have a receiver, and the impedance of my receiving antenna has nothing to do with the transmitter. Well, everything's really tightly, closely lumped together, right? So if I do poor decisions here about how much power I draw off, it's going to affect how much power I get, and it's going to affect the transmitter. So we have to have this, idea of either frequency tuning or adaptively rectifying, controlling my input impedance. And one of the other big challenges is trying to figure out how to get these antennas, these big coils that you saw out in free space, next to these big sheets of metal, and having them still keeping the efficiency. All right. So, what I talked about here is basically the high power, which you just saw, tens of watts, kind of still an experimental level. And then we have the far field, so now we have this citywide harvesting technique. All right. Thanks.
So, we have time for one question again. Do we have any questions for Alanson? Oh, one from Jorge. Hang on. Oh, I'm sorry?
No, sorry. I was talking to our sound guy.
Okay, no questions. Oh.
Regarding the experiment on the TV station, I'm wondering if the switching from signal to digital, by understanding that some stations could lower the power. So does that affect experiment, or it could have been better before the transition to digital?
So this is all on the digital side, digital TV. So I don't know how much better it could have been with the analog. Could have been.